Welcome to a deep dive all about quantum computing. I know, it sounds kind of
A
intimidating.
little bit, yeah, like something out of Star Trek, maybe?
Right. And the science can get pretty complex, but that's what we're here for, to break it down for you, make it clear.
And dare we say, even enjoyable.
Exactly. Now, to get us started, our material today uses this analogy. It says, imagine a regular computer. Think of it like a bicycle.
Okay, I like where this is going.
Reliable, gets you from point A to B, does the job, right? But then it compares quantum computing to, well, a teleporting unicycle driven by Schrodinger's cat.
Okay, I'm definitely intrigued, although maybe a little confused.
Right, it's a pretty wild image. But the point is, they're trying to show just how fundamentally different these two types of computing really are.
At their core, it's about how they process information, right? So your laptop, your phone, all run on bits, like a light switch on or off, one or zero.
Simple, straightforward.
Exactly. But a quantum computer, it uses these things called qubits. And here's the wild part. A qubit can be in multiple states at the same time.
Wait, what? How is that even possible?
It's kind of like, imagine a coin spinning in the air.
Yeah.
Is it heads? Is it tails?
Well, until it lands, it's kind of both.
Exactly. It's
Yeah.
both and neither at the same time until we stop it and force it to be one or the other. That's what's so fascinating about qubits. They can be a 1, a 0, or both simultaneously.
It's like in our source where they talk about, like, ordering a pizza. You'd be able to try every single topping combination all at once.
That's a fun way to think about it. It's not really about literally trying every pizza topping, but it illustrates the point. Quantum computing isn't just about doing things faster. It's about exploring possibilities in ways that were impossible before.
Okay, so it's not just speed, it's about entirely new computational dimensions. I think I'm starting to get it.
It's a lot to wrap your head around. And it gets even weirder, because then we have to talk about entanglement.
Yeah, that's the part that seems even more out there. Like you have two of these spinning coins, right?
Yeah.
And somehow they can influence each other instantly, even if they're miles apart.
You got it. Entanglement is this mind-bending link between qubits. No matter how far apart they are, if one qubit chooses to be heads, the other instantly becomes tails, like magic.
Okay, that is wild. But it sounds like more than just a cool science trick, right? What makes entanglement so important for quantum computing? So entanglement, it's like this secret handshake between qubits, letting them work together in ways regular bits just can't. I'm starting to see how that could lead to some serious computing power.
It's not just about raw power, though.
Oh, right, right. It's about what you can actually do with it.
Exactly. We're talking about solving problems that are impossible, even for the most powerful supercomputers we have today.
Okay, so like what kind of impossible problems are we talking about here?
Imagine designing new materials at the atomic level, or developing personalized medicine tailored to your unique DNA. These are the kinds of things quantum computers could revolutionize.
Now that you mention it, our source talks about simulating complex molecules and how this could be huge for drug discovery, right?
Exactly. Think about it. Developing new drugs takes years, decades even, and it costs billions of dollars. A quantum computer could potentially simulate how those molecules interact really precisely, leading to new drugs and therapies much faster and cheaper.
So instead of taking decades, it could take, what, a fraction of the time? That's incredible. And with way lower costs, too.
And it's not limited to medicine. We could revolutionize material science, create materials that are stronger, lighter, more efficient than anything we have now. The applications are almost limitless. Renewable energy, space exploration.
It's like we're on the verge of a whole new era of scientific discovery. But with a technology this powerful, we have to talk about the potential downsides, too.
You're absolutely right. There are always two sides to the coin.
Our source mentions cryptography, for example.
Right, because right now, we rely on encryption to protect everything, our online data, our financial transactions. A quantum computer powerful enough could potentially break through those security measures.
Okay, so there is a potential for misuse. For malicious applications, that's definitely something to be cautious about. But let's focus on the positive for a moment. The source also talked about quantum computers solving a Rubik's Cube insanely fast. How does that even work?
It all comes back to that idea of superposition we talked about earlier. A regular computer has to go through each possible solution one by one. A quantum computer can explore all of them simultaneously.
It's like having billions of hands all working on the puzzle at the same time. That's mind-blowing. But for all this talk about speed and power, our source also mentions some serious challenges in building these things. It makes them sound really delicate, like one wrong move and the whole thing falls apart. It really does sound like they're these incredibly sensitive machines. What makes them so fragile?
It all comes back to those qubits.
Ah, right, because they're so good at multitasking.
Exactly. Maintaining that both at once capability, that superposition, it's incredibly difficult.
I can imagine.
Even the slightest disturbance can throw the whole system off.
So what are we talking, like a loud noise?
That's one possibility,
Mm-hmm.
but it could be anything: heat, vibration, even a stray particle.
Wow, a single particle could mess it all up.
It's a delicate dance, that's for sure.
So how do you even begin to address that?
Well, right now, a lot of research is focused on making qubits more stable, less prone to errors.
Making them a bit tougher.
Exactly. But it's a huge challenge. It requires advancements, not just in quantum mechanics, but in materials science, computer engineering, so many different fields.
So it's a real team effort.
Absolutely.
Yeah.
And then there's the question of scale.
Right, because right now these quantum computers are still pretty small, aren't they?
Exactly. We're talking a few hundred qubits, maybe. To unlock their full potential, we need thousands, millions of qubits working together. And that brings a whole new set of challenges.
So it's not just about building one super powerful quantum computer, it's about creating systems that can handle all that complexity.
Precisely. It's like we're building a whole new internet from the ground up. But despite the challenges, the progress we're seeing is incredible.
It does feel like we're still in the early stages, kind of like the early days of computers when those machines took up entire rooms.
A very apt comparison. We might not all have quantum computers on our desks next year, but the impact of this technology is going to be huge.
It's been amazing diving into this with you. So for our listeners, for anyone who's just as fascinated by quantum computing as we are, what's the one thing they should keep in mind as this technology develops?
That's a great question. I think the biggest takeaway is that quantum computing isn't just about faster computers. It's a fundamentally different way of processing information, and that opens up possibilities we never could have imagined before.
So this isn't just about doing things faster, it's about doing things that were impossible before.
Exactly. As we keep pushing the boundaries of what's possible, it's important to stay informed, ask questions, and really think about the implications of this technology.
Absolutely. Because one thing's for sure, the future of quantum computing is going to be anything but boring. It's been a pleasure exploring all of this with you.
The pleasure was all mine.
And to everyone listening, thank you for joining us on this deep dive into the quantum realm.